everyone. This is Professor Chen, Mechanical Engineering, and today I'm going to give you a 5-minute head up of the Chapter 4, Pure Bending. And first of all, I'm going to introduce the material model we're going to study in pure bending. And here you can see I bring a model here, and basically that has a rectangular cross section. So here our model we're going to consider in this chapter is all the model that has a cross section that exists, a plane of symmetry. For example, here this is a plane of symmetry, this as well. And for example, we considered a different cross section like trapezoidal. So this is a plane of symmetry. And for example, here we can consider this kind of the shape. So here the plane of symmetry is here, etc. You can deduce. So now this is a plane of symmetry, and about this one, we bending applied is bending applied to these orientations, or we can curve down, we can curve up. Okay, so let me pick up the curve down as one example here. If you look at this model carefully, once I curve down, you can feel the fibers or the lines on the top because of elasticity. The line on the top basically will be stretched. The line at the bottom side here, they're going to be they get shortened a little bit. So let me draw the material model here. So this is the model we call the beam, and this is the front view. Again, this model, the cross-section view, you cannot see here, but let me turn over here. This cross-section must have this feature, have the plane of the symmetry here, and about which we apply the bending, and that is called the pure bending. Okay, so again, the top portions, due to elasticity, the top portion, this line here, going to stretch a little bit, and the lower portion here going to be deformed and get shortened a little bit. So assuming this beam didn't fracture, so everything will remain its integrity. So here you can see this is the distributions of the deformations. So in certain portion that is stretched until reaching to 0, and beyond that one they're going to reduce. So negative strength. So here is negative. So from here you can see here we hit the distribution from the top is positive, means increasing in dimension. The lower portion is negative, that means decrease in portion. So the number change from positive to 0, we must hit certain position that has 0 deformation. So let me connect the points that corresponding to 0 deformation here. And schematically, you can see I use this line, the green line, representing the position where the deformation is 0. This is a very important feature here we call the neutral surface. Neutral surface, basically here I draw the green line, but in 3 dimensions, basically the green line will constitute a plane. Inside this beam, we call the neutral surface. Intersections of the neutral surface to the cross section here, as I shown, is the black line. And let me show here the neutral surface intersecting here. And for this one will be here, and the neutral surface intersecting to this cross section will be here. So intersections of the neutral surface to the cross section is we call the neutral axis, and sometimes we call the NA. Okay, so that is the MA. That is the MA. In this chapter, the first important task you need to accomplish is to recognize existence of the neutral surface or neutral axis. By definitions, the material point on those will be 0 deformation. If 0 deformations, that means divided by original length. So let me say the original length of the beam is L divided by L, and by definition that is strength equal to 0. So by definition, on the neutral surface or on the neutral axis, the strength equal to 0. Okay, so that is the very first important concept you're going to learn. And everything will be depends on here. Then we're going to learn how to calculate. From here, you can see this is the distributions of the deformation divided by length. Basically, that is a strength. So here, this one also showing is the distributions of the strength. And in particular, you can see this strength is normal to the cross section. So here we really talk about is the normal strength. So also that is the distribution. If we multiply strength by Young's modulus, that representing is the normal stress. Okay, so basically here this distribution also represent is the normal stress. And in these chapters, you're going to spend quite a bit of time to learn how to calculate this normal stress. And sometimes people call this is called the bending stress. And the two terms are exchangeable. And here in magnitude sigma of the normal stress or bending stress, you're going to learn this formula is my over I. And this is the magnitude. And this formula you're going to learn is this. M is the bending we applied, and Y is this one. If say you're concerned about the point at point A here, let me say the point A is here. And so the meaning of Y is the distance from A to the neutral surface, the neutral axis. For example, if you want to calculate, say, point B, again, we use the same template of the formula. For example, if B will be here, let me use the different color here. So say if B is here, then you simply measure the distance from the point of where you're interested to the neutral axis. That is the Y here. Okay, so that is the value of Y here. And so you can designate any point in the cross section. You simply measure the distance to the neutral axis. That is the meaning of the Y. And what is I? I is a moment of inertia about the neutral axis. Okay, so that is very important. The very first step, you need to identify where the neutral axis is. And so this is the magnitude of the neutral axis. And then in this case, you're going to learn, in particular, if for this cross section, the bending is bending curved down like this. So from here, you can tell the upper portion is being stretched. So the material points in the upper portion here above the neutral axis is under tension. Below is under compression. So from here, you can identify, for example, point A and point B will be calculated here is in tension. So here you have to artificially add up the positive sign. On the other side, if you're going to calculate the stress at point C, for example, point C is here. So in magnitude is my over I, and again, y is the distance from here to here. And here you can see C falling into the negative range. So here you simply put an artificial sign indicating that it's compressive stress. This is the very first important concept in these chapters, and then the remaining focus will be applied to other the practical situation. For example, here let me using this one. Say if this portion is made of say aluminum, the lower portions is say made of the say copper. So this is we call the composite materials. How to apply the fundamental information to composite material we're going to study here. And then also we're going to study is another situation. Let me utilize the information here. So for example, if we have the chance, say the axial, the loading applied is not vertically, it's not horizontally, but the bending is applied in any declined orientations. How to apply the fundamental information, the formula to solve this one, that is another big concept, big topics in these chapters. And pay attention, this one is we call the unsymmetric bending. And that will pretty much constitute the whole learning goals of these chapters. Thank you.